All right, today's lecture is on the solar system. Early astronomers knew about the basic stuff: the moon, stars, Mercury, Venus, Mars, Jupiter, Saturn, comets, and meteors. Now we know, and this isn't even current, there's a lot more that we've discovered. Solar system has at least 165 moons, one star, 8 planets. We added Uranus and Neptune, 8 asteroids, and more than 100 Kuiper belt objects more than 300 kilometers in diameter, smaller asteroids, comets, and meteoroids. This says more than 200 extrasolar planets have been found, so these would be exoplanets. That number has grown immensely. We're now in thousands of planets, so you can see how much we've learned quickly. Understanding planetary formation in our own solar system helps us understand its formation as well as formation in other systems. So when we measure the planets, we look at things like the distance from the sun, the orbital period, the radius, masses, rotational period, density, and all this stuff we can get from a wide number of sources. And here's just information on each one. Obviously, you don't need to memorize all of this stuff. And here's the overall layout of the solar system. One view from the top, as if you were looking straight down on it, and one view from the side. And what you see here is that from the top, you can see how much stuff is really bunched into the middle, and then you get further out and it spreads out a lot. And here's the Kuiper belt out here. So from the side, everything's on one plane. As you get stuff spinning, it tends to flatten out, and so has the solar system. So the solar system is flattened out, and it's for the most part in one small plane there. Because the planet's orbits are close to being in a plane, it's possible to see them in what we call the ecliptic, which is a relatively straight line through the sky. And this picture is just showing an event where you had Jupiter, Saturn, Mars, Venus, Mercury all kind of lined up. And actually, if you follow, the sun would have just set over here as well. More precisely measuring things, we can convert angular diameter to radians and multiply the distance. We can get the mass by measuring the distance and orbital speed of a planet's moon. And we can get density by dividing mass by volume. If you want to pause it and take a look at this slide, it just goes through the differences between the terrestrial planets and the Jovian planets. Terrestrial planets are the Earth-like rocky planets. Jovian planets are the gas giants. So differences among them: all have atmospheres. But they are very different. Surface conditions vary a lot. Only Earth has oxygen in its atmosphere and liquid water on its surface. Earth and Mars spin at about the same rate. Mercury is much slower. Venus is slow and retrograde. Only Earth and Mars have moons, and only Earth and Mercury have magnetic fields. As far as interplanetary matter goes, there are a ton of asteroids and meteoroids. And they have different compositions. Most of them rocky. Asteroids are bigger. The asteroid Eros is 34 kilometers long. So obviously it would be a bad day if that slammed into something. Comets are icy with some rocky parts. This is a picture of the Hale-Bopp comet. Interesting here is you can always tell where the sun is because this tail is not from the movement, but the tail actually points away from the sun. Pluto was once classified as one of the major planets, is the closest large Kuiper belt object to the sun. You can see here that Pluto has a bunch of moons. This one, the closest one, is called Charon. Normally we would talk about why it's not anymore, but basically Pluto and Charon are too close in mass, so they kind of orbit around a central point in between. So they're orbiting that as well as the sun, which kind of does not meet the definition of what a planet is. As far as spacecraft exploration, this is one of the things that we would have talked about more in class. It's kind of interesting because you kind of see the paths that things take when you go to launch something towards Mars or Venus or Mercury or whatever. You don't launch it in a straight line. You actually have to come up behind it. So this is showing when you're trying to get to Mercury, you launch here. use Venus's gravity to pull you into the inner solar system, and then you come up behind Mercury over here. The Soviet Venera probes landed on Venus from 70 to 78. They didn't last very long. I think the most successful one lasted like 10 or 15 minutes, and they got a few pictures. So we have mostly done orbiters. We're taking images down of Venus. Mars is probably the place that we've done the most exploration as far as planets. Lots of rovers and landers and all sorts of things. This is just kind of showing you what the typical orbital path is to get to Mars. Once again, you have to come up at from behind. So you launch here and then you come up like that. This is a picture from the surface of Mars. Lots of interesting things. This had airbags so that it would protect it on its way down. Notice the names of all the rocks. Apparently the guys at NASA had plenty of free time. This Pioneer and Voyager both all kind of look like this. And they kind of took off and they flew through the outer solar system and kind of took pictures and sent them back to us as they went. These are some of our more opportunistic and successful missions that we've had. And we used gravitational slingshots to get them where they were supposed to be. This is showing Cassini mission. Let's see. How does the solar system form? This is the next important part here. So it's from nebular contraction. So talk about nebulas, and you have the big cloud of gas and dust here in space. And then as it starts to spin, it flattens out. And then as collisions happen within that flattened disk, eventually certain areas collect more mass than others, and those are what end up becoming the planets. And that's it for this presentation.